Welcome everybody. I'm glad to see the interest in ocean-based CDR. I think it is beginning to really rise on the agenda of awareness for people in the ocean community and in the climate community and in the CDR community. So that's a good thing. It's still not necessarily where it might deserve to be, but it is growing in sort of recognition. I have been in the environmental community for a long time. I recently left World Wildlife Fund, where I was leading the ocean program, to create an entity called the Ocean Climate Trust, based on it's essentially created around the proposition that the ocean agenda needs to be significantly amended with a climate remediation focus, and the climate agenda needs a much stronger ocean focus, and that at the end of the day, oceans and climate are really two words for the same thing. They're just different parts of a global system that regulate our planet. And the disconnect that we've been seeing in sort of policy and action really needs to change and be disrupted. And part of that disruption is that we need to have a much broader recognition throughout the entire environmental, ocean and climate community of the need for drawdown. And that's nothing new to anybody on this call, but we do not represent the dominant view by any means. So we really need to raise the level of awareness of carbon drawdown to begin with. But even as we see that awareness growing, it's almost entirely focused on terrestrial approaches. And it's hard to figure out exactly why that is. I think we are just such terrestrial animals that we gravitate naturally to what we know, and the oceans are far away from most of us and mysterious, and we don't fully understand how they work. And so we haven't been rallying to the possibility of ocean CDR like we might have. But I think also there's been a false precept in the environmental community that somehow the oceans they should be off the map for climate remediation and for climate action when it comes to things like drawdown, and that somehow they are pristine, which of course nobody believes they are, and we know that they are the most impacted systems from the buildup of atmospheric greenhouse gases, but that has stopped progress. However, over the last couple of years, there's been some pretty significant shift to see more of a discussion of ocean CDR. There was a report published last year, and Greg Rao, who is on this Zoom, was one of the authors from GSAMP, G-E-S-A-M-P, an advisory body to the UN that looked at a variety of ocean-based approaches to carbon drawdown. Unfortunately, they called it geoengineering. I think we need to completely separate pollution cleanup from geoengineering, but that's another topic. But it highlights a number of ways that you could employ the biological pump and power of the ocean, or just its current storage of CO2 passively, as a way to reduce atmospheric CO2. A number of those are still fairly experimental. You have a range of topics from large-scale macroalgae cultivation to assisted upwelling, assisted downwelling, ocean alkalinity enhancement, advanced weathering, and a variety of other approaches. We are now, Greg and I, leading an effort under the auspices of the Energy Futures Initiative to develop a policy roadmap for the US government around ocean CDR. And we are also, myself and others with an organization called Ocean Visions, going to lead an additional road mapping exercise to try to really identify what the critical pathways are in each of these areas. What do we need to ask and answer and to try to resolve in order to see whether or not we can scale, let's say, large-scale macroalgae cultivation, or iron fertilization, which is one of the topics on the list. What do we need to know about whether or not that is ultimately going to be a contributor to CDR, about chemical stripping of CO2 from seawater? So I propose this discussion as a way to, first of all, identify people in the field who are interested in these topics, and then put these questions out to you for this time that we have about what are some of the most promising and innovative and highest potential approaches in the ocean CDR space. What do you see as the most critical obstacles in the way of moving those forward? And those could be engineering, it could be political, they could be ecological, anything. And what would you propose we might do about those? So sort of three questions. What are the most promising approaches from your perspective? What are some of the most critical hurdles and issues that they face? And what might we do to try to advance those? So I don't have any particular proposal on how to structure this conversation, but I wanted to put that introduction out and put those three questions forward. And then maybe just so that we don't have people tripping over each other, maybe we could use the hand function and Coulter could essentially moderate the discussion to some extent.
Yep, so just as an initial starting point too, Remy asked a question, if we want to start with questions, where Remy asked, can you comment on the role of the recent Ocean CDR paper by CEA, ClimateWorks, and the connected effort by Antonius? He said he believed Greg was part of the effort.
Yeah, I can comment a little bit on that. So the paper that CEA did and the workshop that they held, and Greg was part of that, was around ocean alkalinity enhancement almost exclusively. And there's a paper out on that now, and I can probably put a link to it in the chat box soon. ClimateWorks continues to fund and be interested in ocean CDR, and so they are funding the EFI initiative that I mentioned. Greg and I are co-chairing. They funded, it looks like they are going to be supporting a National Academy study on ocean CDR, and they are supporting, we hope, this work by Ocean Visions on road mapping. So they are the key player. And the work they did on ocean alkalinity enhancement, I think, is a great start. And maybe Greg could comment about that product and its utility and how we might use it going forward.
Okay, thanks, Brad. Can people hear me?
Yes.
Okay.
Yeah.
Yeah, I was part of that. I and probably 15 other people were involved in that. And yeah, it was focused on ocean alkalinity. Obviously, there are other approaches to marine CDR. The focus of the report was really on philanthropies and how they could get involved and why they should get involved in funding research on things like ocean alkalinity, which was the focus of that report. So I think it was encouraging that NGOs are starting to step forward and support thinking and also hopefully support research in this area. And yeah, happy to answer any other questions that people might have.
I just put the link to that document in the chat.
Okay, so Greg, I recall from your previous conversation or the presentation that you made at Many Labs, probably just over a year ago, almost a year and a half ago now, discussing, I believe in that one, you're focusing on ocean alkalinity too. I think for those of us who are less familiar with ocean CDR, when we talk about alkalinity, when we talk about iron seeding or fertilization, upwelling, downwelling, of those, are there ones that currently have a lead? And if we consider what potential negative impacts they might have, what does that look like? I don't know well enough to direct that conversation, but those are some things that I know in conversations have come up as concerns around these practices.
Mm-hmm. Well, certainly any marine CDR approach is going to have positives and negatives. At least some of those we don't know very well what they are. We suspect that we can suspect what they might be depending on scale, et cetera. But I would say in most cases, we need to do more research to really fully understand what the real benefits as well as the negatives are, so that we can ultimately make intelligent decisions as to how or if to go forward with these various marine CDR approaches.
There's maybe just to jump in on that, Coulter, there's a continuum, right, of potential impacts, and it starts from the absolute minimum and completely proven positive, which I would put all coastal blue carbon into, which is restoring mangroves, seagrasses, salt marshes, coastal wetlands. There's absolute evidence that that is highly beneficial on multiple fronts. Kelp forests, which have been decimated in many parts of the world. So that's, that starts at we know this is something we should be doing. It's a no-brainer. We should be getting after it very quickly. And then they move into a continuum of things that become more and more complex and require a lot more science and testing and development to understand what kind of impacts they're going to have. But we can't spend decades doing the science, right? It's got to be very applied science. We need to be testing these things and in application as much as possible, because the no action alternative in the oceans right now is so bad that almost any other scenario, it's hard to imagine many scenarios being worse than what's going on in the oceans right now in terms of the superheating of the ocean and the corrosive, the changes in ocean alkalinity.
Absolutely.
So how do we change the kind of intensely regulated environment that allows for much freer experimentation? And it seems to be the policy side of that has been a major constraint, was certainly when we talk about, ocean particle seeding. I mean, some of the hysteria around that has seemed completely insane to me, given the small scale of the experiments. But somehow, similar to what I sort of think on advanced nukes, we actually have to take some risks here, and we have to change the mentality. And I just don't know if we made any progress at all in that.
Well, I would just say that that regulatory environment varies greatly by country. And there's a lot of countries with massive ocean zones who have a different approach on the challenges of the ocean. Many of the Pacific Island nations, for example, have it's an existential threat to them, and they have a little bit more of a flexible approach to testing and developing some of these things. I would not suggest US waters would be the first place I would ever want to try to test and develop anything. It's extremely difficult. Not impossible, but very difficult.
Yeah, and I just want to kind of echo the question, I guess, something that we're thinking about a lot as well. Project Vesta, for those that don't know us, and hi, good to see you, by the way, Brad. We're a coastal enhanced weathering nonprofit, and we exist to advance the science of that field, which of course involves these beach nourishment experiments where we grind down olivine rocks, take them to beaches, deploy them there, and measure everything that happens on the beach and in the water. And we believe we found our first pilot site, but we are very much looking to figure out which are the friendliest countries to do these kind of experiments. So if anyone else has perspectives on that, certainly welcome.
So, Brad, I guess I'm Phil Kithill with Ocean-Based Climate Solutions. And I guess what I should do is give an update on what we are thinking. So we have developed a wave-powered upwelling and downwelling pump. Brings up water from 500 meters, or it could bring up from any depth, but our target depth right now is 500 meters in the open ocean, and downwelling to 600 meters in the open ocean. One device doing both up and down. So we are looking for funding to do some full-scale testing. And on an ideal scenario, we would raise $8 million tomorrow and deploy 70 of these devices. We call that 4 arrays. An array is 2 per square kilometer in a 3 by 3 kilometer grid. So take that times 4. We measure the effects using, or we'll do that using the new biogeochemical Argo sensors, which are just coming online. And so that's our measurement and also validation strategy. We've had our technology looked at by a couple of very skilled scientists at the German Marine Research Institute, GeoMar. Andreas Aschliess, one of the leaders in modeling ocean deoxygenation, ocean oxygen. And they ran a model and they found, it's more complex than I can say in 1 minute, but basically would be beneficial to ocean oxygen, at least on the short and medium term. And longer term, who knows, because the models diverge over longer time periods. And that was based on a higher density, greater volume pumping than what we anticipate. So anyway, I relate that to you. And the other one is Ulf Riebesel at Geomar, who's done both upwelling and downwelling ocean testing. He just returned from Peru doing an ocean experiment. He'll be in the Canary Islands next spring. And he too is positive on what we are doing. Again, knowing there are some longer term effects that you don't know until you do it. Both of them take a broader perspective than just carbon dioxide removal. We're talking about ocean ecosystem restoration. And so, as you know, the oceans are warming, they're getting more stratified, there's less primary production, oxygen content is going down. Bad news for us. Everything's bad news for us. Of course, the fish are depleted, both through less primary production and more overfishing. So a whole host of problems with the oceans. And so the technology that we're pursuing could play a role in restoring the ocean ecosystem. And then, of course, there could be some negatives. We'd have to find that out. The second part of it has to do with how do you pay for this stupid thing, not stupid thing. And our approach is called stock for carbon. So we would go to large multinational public corporations, say with our technology, we can restore the ocean ecosystem and also sequester CO2 as part of that primary production. We think it might be X tons per pump per year, but we'll find that out. It'll vary from place to place. And we can, if we install a large number of these widespread across the open ocean, reduce or eliminate your carbon footprint, Mr. Corporation, and we want you to pay for that. It will be expensive, so pay in stock, not cash. If you were to pay in cash, it would wipe out your bank account in 3 or 4 years and you go out of business.
Hey, Phil.
And yeah.
Sorry, I just want to make sure we give other people a chance too to chime in here.
Okay, so that's my last sentence. Stock for carbon is our approach to funding.
So
That's great.
I'll hop in here too, because I think this brings up a point, you know, in Phil talking about the more technical elements of what they're trying to do and how they're going about it. Just even from a broad standpoint, I know that there are a number of people who are in this session because they want to learn about ocean CDR, coming to it from a perspective where they don't know anything about it. So we talked about the continuum of, you know, nearshore, you know, blue carbon systems all the way on that spectrum. I think some of us have a familiarity with iron fertilization because of that stunt that got pulled a few years back. Brad, could you give us like a potentially quick overview of the different technologies and their intended application? For example, what does upwelling and downwelling actually intend to do, or what benefit does it intend to provide?
You know, I'd let Greg do that, given his authorship on the paper that looked at all of these approaches. Keys.
Okay, well, no pressure. I'll just,
Yeah, sorry to just throw you under the bus there, Greg.
yeah, okay.
Just on a surface level, just so people who are new to ocean CDR have some perspective on the different technologies we're talking about.
Okay, so ocean upwelling. The intent there is to bring nutrient-rich water to the surface that would then fuel additional photosynthesis, that would then consume more CO2, that would then form biomass, that would then sink into the subsurface ocean. That's the general idea. The problem with that, in my view, is that not only do you bring up nutrients from the deep ocean or subsurface ocean to the surface, you also bring up CO2. And So what you really need is photosynthesis that's going to counterbalance that CO2 that's going to be released at the surface as it comes, as it's upwelled, so that in fact you do have a net consumption of atmospheric CO2. And that's a little tricky to do. There's ways you can do it. One is to sort of change the ratio of the carbon to nutrients that are taken up by the photosynthesis, so that in fact you do take up more carbon than what will come up with the upwelling. So you, in theory, could have a negative emission scheme doing that. I mean, also artificial upwelling. I mean, it is artificial, so it is going to impact the ecosystems wherever you're doing this. You're going to potentially change it from an oligotrophic open ocean setting to one that's suddenly nutrient rich, and that potentially can totally change the food web for good or for bad. So that is a concern there. So are there any further questions on
Well, hey,
the
Greg, maybe,
upwelling concept, or have I missed something?
I was just gonna say, maybe we could do it at a much higher level than that. Just lay out kind of what the big approaches are. I think they all have different challenges. Some are, some are much more understood than others.
Well, I would say at the first taxonomy level, there's biotic and abiotic. The biotic approaches to CDR, more or less build on what I just said. That either you're trying to restore photosynthesis and therefore, consume CO2, make it into biomass, and then hopefully that gets stored or sunk somewhere. Or you're trying to increase photosynthesis over and above what it has been or what it is, and again, make biomass, and that hopefully sinks to the seafloor and is buried, or is somehow harvested and somehow carefully stored so it doesn't return to the atmosphere as CO2. And there are various marine photosynthesizers that can do this. There are algae, cyanobacteria, there are macrophytes, seagrass, et cetera, that all the range of marine photosynthesizers that potentially could participate in this kind of a scheme. On the abiotic side, there's really, in my view, two general categories. One is chemical, and that usually involves adding a chemical base or an alkaline material that reacts with CO2 to consume it out of the water, or to transform it from CO2 dissolved in water into something like bicarbonate or carbonate, which is not CO2 and which is not easily exchanged with the atmosphere, although it can exchange with the atmosphere, but it's a more stable form than simply molecular CO2. And there's various ways of adding this alkalinity or base to the ocean. You can, some people advocate adding alkaline minerals to the ocean in very fine particulate form, which are very slow in reacting, but if you have enough of them and they're small enough in size and they have a large enough surface area, in theory, you can invoke a chemical production of alkalinity that will consume CO2 into these more stable forms. Other ideas include making synthetic base or synthetic alkaline materials. Of course, chemical bases are very important for our life, for industry, for synthesis of lots of stuff that we use. So it's well known how to make this material. What's more difficult is doing it cheaply in a large scale and doing it in a way that has a low carbon intensity, because if you spend a lot of energy making these chemicals to add to the ocean, then the carbon footprint of that could completely offset what it is you're trying to do, and that is absorb CO2 out of the air. So some care is needed there. Also, we have very little experience in actually adding synthetic bases to the ocean. So certainly more research is needed to understand what the effects of that are on ecosystems, on biology, what the limits are to doing that, how dilute does it need to be. But on the flip side, there could be a real benefit there because it helps counter ocean acidification. The ocean is naturally acidifying because our CO2 is passively diffusing into the ocean, dissolving and generating carbonic acid. By adding alkaline material, you are helping to counter that acidification. So there's a potential benefit over and above carbon removal and storage to adding alkalinity to help counter that acidity. And then lastly, there are physical ways of removing CO2 from seawater. Just as Klaus talked about today, removing CO2 from air, removing CO2 from water has more or less the same effect as removing it from air, because the two are more or less in equilibrium. So if you're removing CO2 from the ocean, that'll undersaturate the ocean in CO2, and CO2 will then invade from the atmosphere. So I've always been interested in why not using the largest rather than making air contactors, why don't we use the largest air contactor on Earth, which is the ocean, and simply figure out ways of removing CO2 from that solution and not worrying about, all these machines that are going to consume very dilute CO2 out of the air.
Yep.
We can consume it actually it's a much more concentrated solution in the ocean, and therefore affect carbon dioxide removal without actually removing it from air directly. It's an indirect approach to air removal. And I think that's something that needs to be explored that would complement or possibly outcompete direct air capture. So I guess that's in a nutshell my CDR taxonomy, and I'm sure I missed something.
Yeah, and people can look at that GSAMP report that I mentioned and get a pretty good grounding if anybody wants more kind of basic understanding.
Can you put it in the comments?
Yes, I'll do that.
Okay, Greg. Well, I appreciate that overview of everything. So, I think within that, so those are kind of the umbrella categories in terms of biotic, abiotic, and then physical extraction. One of the things I know we have Tom from Project Vesta here too, and they work on advanced weathering, which is one of the presumably abiotic approaches. Tom, would you care to give a little bit of an overview of how you guys are thinking about this and what your approach entails?
Yeah, absolutely. Yeah, and Greg, by the way, thank you for those.
Oh, sorry.
That was a extraordinary. That was probably one of the clearest summaries I've ever heard of the taxonomy of ocean CDR. So thank you for that. Yeah, Colter, thank you. So it's essentially Project Vesta. We're a nonprofit, and we exist to further the science of coastal enhanced weathering. So that's within the abiotic category that Greg was talking about. And specifically, what we do is we take olivine rocks, which are mostly magnesium silicate, and essentially when they dissolve in solution, that causes an increase in alkalinity in the ocean and pulls the dissolved carbonic acid across to become bicarbonate. And this is the main mechanism that over geological time, carbon dioxide has been captured in limestone rocks. And if this hadn't been happening, then the carbon dioxide that comes out of volcanoes would have basically built up in the atmosphere, caused a runaway greenhouse effect, and we'd now be living or not living on a planet that looked like Venus. So the question is, how do you accelerate that natural process? And coastal enhanced weathering takes these olivine rocks, brings them to beaches and shelf seas, and allows the wave action to break them down. And Greg made an important point about what's the carbon efficiency here. So, how much carbon do you emit in the process? And of course, that's something we all need to look at for any CDR technology. Our estimates so far, and these are only estimates, I want to be cautious about that, are that we can capture about 20 times the carbon we emit in the process of quarrying, transporting, and milling the olivine down to micron or submicron size. And you know, the key to that, of course, is the fact that the waves are what break down the sand into smaller and smaller pieces, and ultimately ending up in solution. So yeah, that's an important point. One other thing I just want to say about it before I kind of I want to make sure others have a chance to comment is one thing that I just personally like about the abiotic approach is that I think it's harder to imagine losing control of it. You know, when you have you know, I think we should be exploring all approaches and being very cautious about any kind of interventions. But, you know, when you're introducing biology into systems, you know, that's a self-replicating entity that can grow exponentially. And, you know, there's now a lot of rabbits in Australia. And you know, you and beavers in Patagonia and all sorts of stories, and you just want to be very cautious there. The good thing about these geological interventions is that if there are unintended consequences, and by the way, we're currently working on getting our first real-life beach pilots up and running after a lot of lab experiments have been done over the past few decades. But you know, if something goes wrong in those studies, then you let the olivine dissipate and everything will presumably return roughly to normal. And that's not necessarily the case with biological interventions. So that's something I personally like about it, alongside the low cost and the high scalability of what we do.
Great. Well, I appreciate that overview. I think that's really helpful. I had heard of Project Vesta before and, you know, some of the high level stuff, but I think that gives some context on how you guys are thinking about it and what your approach is in terms of balancing not only the carbon it takes to get the olivine rock, but then what the return is and how it's kind of self-regulating by being abiotic. So I know we also have Jeff Chapin in this room. Excuse me if I mispronounced your last name there, Jeff. And you're working with kelp, which is one of the biotic forms. Would you care to speak about that some?
Thank you very much. I appreciate that. I would love to, and appreciate this panel and the discussion and the overviews. I agree that was a very coherent overview of CDR, and appreciate this group and all the work you've been doing. What we are, C Combinator is taking the biotic approach, where we have Brian von Hertzen developed a way to use renewable power in the ocean to upwell from the deep, nutrient-rich water into a large, essentially a hydroponic horizontal array where kelp is grown on a substrate. And how we do that, I think, is very cost effective. I joined him about 6 months ago to run the commercialization of that work because I saw that it was featured in Project Drawdown, Paul Hawkins' work, and I've always felt that it's a scalable, natural, low-cost solution. What we're doing is, the exciting part for me, the reason why I joined, is that we can actually grow the kelp, process it through both non-proprietary and proprietary methods, and valorize the kelp into 6 different products with quite a lot of value. And then we can also, the leftover or just initial kelp we grow can be sunk below the thermocline. So we can grow large amounts of kelp. We can process it for much more than in revenue than it costs to grow it, and sink the remaining kelp and the remaining end product to drop significant tons to below the thermocline, where it will be locked away for hundreds of years or more. And so there's still some science to be done on the testing of that, of course, but everything points to that working. And at the end of the day, what that does is it allows us to have a negative cost to sequester a ton of carbon. So companies and others can literally fund these large arrays in the ocean, offset their carbon, and earn a return. And so if we're successful at that, and there are certainly we have work to do to get up to scale, but if we are successful, we're hoping to create a way to earn money while sinking carbon, which could accelerate the financing of the space. And I don't think has been done before, but I would love to be corrected. But we're pretty excited for a negative cost to sink a ton of carbon and turn it into an investment. Thank you for the time. Appreciate it. That's C Combinator's work.
Thank you for that, Jeff. That was really interesting. And I think, now we've had the perspective of a couple different, folks who are working on biotic, abiotic. Greg, what are some of the physical extraction methods? I know you got into that a little bit. I don't know if doing a brief look into that would be helpful in terms of contextualizing abiotic, biotic, and then physical systems.
Hey, Coulter.
Well,
Oh, sorry, Brad.
Yeah, just before we do that, I'm just wondering, I just would love to give other people a chance if anybody has anything that they want to say, especially in relation to, those questions. Anybody else, is there anybody else working on any particular pathways that they feel are, needs some support, needs some attention?
This is Mark Capron with Ocean Foresters, and I don't know how I got that background, but I don't know how to get rid of it as well. We're doing a process where we grow a lot of macroalgae in a complete ecosystem, because you notice that we had to have an ecosystem. We were funded by ARPA-E to develop a macroalgae for energy growing process. And as we were into that, ARPA-E, we actually told ARPA-E we were concerned about nutrient shadow. That's where, the nutrients arrive on the leading edge of your big flexible floating reef and don't make it to the back edge. Okay, but if you have a whole ecosystem, you have a whole lot of critters reconverting all the various nutrients that are available and making them available to the seaweed. So basically, you need to have a whole ecosystem. And the other thing we discovered is that you got a hell of a lot more productivity if you mowed the ecosystem like every couple of weeks. And part of this is because we were in the Gulf of Mexico using Gracilaria, which is stuff that only grows about as big as a basketball. And, instead of kelp like the other teams were using. But it turns out that guy in Florida had done a bunch of experiments back in the 70s and 80s that you could grow this stuff. And if you mowed it every week, you got productivity that was like 3 to 4 times more than people would expect using the way they've been farming kelp at the moment. But let's go back. So people have found out that when they tried to grow macroalgae for energy, you couldn't sell it for energy. People wanted to eat it or eat the related stuff. And so our plan is to set up the ecosystems. Don't even bother to harvest the macroalgae until 8 billion people are stuffed with the other seafood that grows on the ecosystem, the shellfish, the lobsters, the crabs, the oysters. After that, then you keep building it out and people aren't going to worry about seafood. So you can start harvesting the macroalgae. You take it in for hydrothermal liquefaction. The reason for hydrothermal liquefaction is because you get all the nutrients back. If you go to too high a temperature, like gasification or something, you don't get all the nutrients back. So that's the process. You cycle the nutrients quickly. If you do the hydrothermal liquefaction right next to an alum cycle electricity production power plant, you can sequester the leftover carbon. So you actually have carbon negative biofuel. When you're doing hydrothermal liquefaction, about 60% of the carbon becomes oil and 40% of the carbon remains available that you could use as fuel for the alum cycle electricity production. And alum cycle electricity production has a byproduct of liquid or supercritical carbon dioxide at $100. I left a bunch of info on the, what do you read?
On the chat.
Yeah, chat box.
Okay. Anybody else want to contribute in any way?
Brad, I'll say something.
Yeah, David.
Yeah, hi everyone. I'm David Koick. I'm a postdoctoral researcher with Ken Caldera at the Carnegie Institution for Science, and I work on ocean-based solutions to warming, acidification, and deoxygenation. So I think one of the things that you've heard from a lot of the speakers is kind of how you can pair many of these ideas together. And, you know, I think a lot of what these speakers are getting at is that a lot of these things are modular. So you can, you know, you can pick the best pieces of different elements and try to combine them together to create, you know, the lowest cost per ton of CO2 removed or something like that. You know, just as an example, people like Greg have looked at, you know, how you can couple ocean thermal energy conversion with ocean carbon dioxide removal. And you heard from Jeff how you can couple ocean upwelling with macroalgal production. So, you know, there's lots of potential to combine different technologies to achieve, you know, both the ocean carbon dioxide removal that you're looking for, as well as potentially some level of energy production or valorization of products.
Good point.
Yeah, and I guess question going back to Greg and Brad, I think some of what's not clear to the broader public is how scalable some of those things are as compared to some of the quote unquote established paths that get a lot of attention. If you could quickly comment on that.
Yeah, well, maybe I'll just take a quick cut at that. I mean, some of these are eminently scalable, just given the sheer size of the ocean, right? So something like what Jeff talked about with growing macroalgae on artificial arrays that you know, are able to solve nutrient deficiency through upwelling. If that all worked, and if the net ecological impacts were acceptable, you know, that is highly scalable. I think the alkalinity enhancement seems to have very high scalability. If you read that report by CEA that I put on the chat box, it indicates as one of the most promising pathways. Others we just don't know about at this point. Ocean iron fertilization, one of the reasons that it was that so many people have spent a fair amount of time thinking about it is because, again, it is very scalable at potentially a relatively low cost. And it happens naturally already. One of this giant sargassum bloom that we've been seeing in the Atlantic year on year is associated with iron blowing off of the deserts in Africa. So it's not, you know, it's not a completely, it's not a product, it's not a process that's not known to nature. And we just don't know what the downstream impacts are fully of doing any of these things at scale. So that's our most critical challenge is understanding the downstream ecological impacts, making sure that we have good scientific validation, because we'll get caught in a firestorm otherwise, and dealing with the economic issues, right? So one of the things I think there's a real possibility here is to pair these giant commitments that are being made by Microsoft and AstraZeneca and BP and others to say they're going to be carbon neutral or carbon negative. They're going to have to get that from somewhere at the most reasonable cost. And I think the oceans have a real chance of competing in that space, but we need to join those dots. Anybody else? Any thoughts?
Yeah, I guess just following on that, then I'm on the board of a couple of foundations. What's the best way to support the ecosystem? It seems that everything's in between the lab stage to the experimental stage. What are the leverage points here for money to move this forward?
Well, I mean, it depends on what kind of money. You know, there's certainly a need for investment money in some of the potential players. For philanthropic money, I think you know, it's harder to invest in specific businesses as a philanthropy, although it can be done through impact investment or program-related investment. But we have a need to just raise the profile of this field broadly, because it is very undervalued and underappreciated as a pathway to climate action. And so there's definitely things that the philanthropic community can do to help build what I call the social and political license for this space, because it doesn't have that same license as, say, growing trees or doing regenerative agriculture, but yet it has far more potential to kind of reverse the climate disruption that we're seeing because of greenhouse gases. So social political license, certainly, you know, research, we do need research to be funded. We need these external validations to accompany the practitioners that we've heard from, who aren't going to be able to pay for the science at the same time they're trying to pay to put their work out in the field. So I think there's a variety of roles for philanthropy, and I'd be happy to talk to you offline about any of that.
Sure. Yeah, and maybe if I could jump in, first of all, well said, Brad, completely agree. And just from a Project Vesta perspective, we're a nonprofit. We're raising $1.5 million to get this technology to maturity. So Remy, would love to follow up with you offline if that's something that you'd be interested in delving into in more depth.
All right, gang. So I think this has been a really helpful discussion because it's allowed us both on a surface level to introduce people to a variety of the concepts that fall under ocean-based CDR, as well as see some of the faces that we have within our community now who are working on this. We have about 5 minutes left. So what I'd like to prioritize here are any last questions. There hasn't been a ton of action in the questions section here. I know we've done a pretty solid job of covering our bases in terms of the, you know, depth and breadth of this conversation. Brad has put in the link to the content that he was discussing, but let's see if anybody have any questions that they feel would help them to better understand this space or walk away with something concrete. And if not, we can wrap it up with any of the folks who have discussed or, you know, been part of this discussion. Let's wrap this up with what you would want people to walk away with in terms of either a deeper understanding of ocean CDR or how they can be involved in better understanding and bringing it to reality. So questions first, and then we can wrap it up with takeaways.
Hi, so I'm Felix Kramer, and when I talk about drawdown, I talk about kelp, and everybody gets excited about it. And my feeling on all this is we would be so much further along if we actually have even tiny proofs of concept to talk about things on every solution. I see that certainly coming soon with Vesta. I'm really hoping that C Combinator is going to come through quickly with something to really give something specific to people. I spent about 3 years talking about how plug-in hybrids were a great idea, but it was when we converted a couple Priuses and started driving around that people said, wow, why can't we have those now? And I think that's what we really need right now.
Excellent comment.
If I may just reply, thank you, Felix. And we, you know, marine permaculture has been in play for several years, and I think I was glad to be able to now just recently start the commercialized spin out of that technology because it needs commercial capital. And that's what I've done in my past. And I think Brian Van Hertzen, you know, has done a great job with the technology to date, but we needed to scale it and get more progress quickly. So I look forward to proving that. I completely agree. And that's my mission. And we do have proof points in the Philippines currently at small scale, but we need to get to larger scale quickly. We should be in the next year or two.
I think to Felix's point too, we've seen some of the applications of these smaller, you know, integrated aquaculture farms that are trying to, you know, bring kelp into a position where it's more marketable. But to your point, I think those prove it on a small scale, and to really make an impact from a carbon standpoint, we need to scale that up further. So we appreciate the work that you guys are taking on there and making that a larger reality.
100% agree. Thank you. And we appreciate any support. We appreciate this, Coulter. It was a great forum.
Okay, so let's give it a wrap up. Brad, I feel like you've been our fearless captain. Is there anything that you want us to walk away with for a better understanding of ocean-based CDR, where it's headed, and what we need to know to be supportive of it?
Well, this is, thanks for that opportunity. This is a community that already is fully committed to CDR. So that would be, that would be step one. I want everybody to really talk about how important carbon drawdown is to a stable and safe climate. We just have to get that. We've got to stop talking all the time only about reducing emissions. We've got to clean up the pollution. And I want people to take away from this the idea that the oceans can play a really significant role in that, given their sheer size, their photosynthetic capacity, and their role in the global carbon cycle and as a carbon pump. And then get excited about any one of these potential pathways and find out more about it. And we gave a few links that will help you. You can contact me at Ocean Climate Trust, and I'm happy to connect you with people I know in different spaces. But as Jeff said, and Tom said, we need to connect dollars to these initiatives. I mean, let's just get on the brass tacks. Everybody needs dollars as a form of oxygen and sunlight to make this stuff work. And everybody's struggling in that regard. And we need to connect some of those bigger corporate commitments to this field. And so there's pathways there that are really interesting. So that would be my response of what I hope people take away.
Brad, thank you so much. It's time for us to transition back. We have our closing keynote now with Dr. Lisa Dyson. Dr. Dyson is a real badass. And so I'm looking forward to this conversation a lot and her closing keynote. Thank you so much for all of your inputs here.